just so you guys know, I forget, did I post? I can't remember if I posted the class recording yesterday, but I recorded you guys yesterday morning, but I forgot to, because we went right to the bell, I forgot to stop the recording, so I recorded all of second period too, and I went to go look at it, and I was like, oh, this is like an hour and 5 minutes long. That's kind of long. So, so it's not you guys that got posted on the internet yesterday. It was the other class, but you can, if you want to watch and listen to how the other class lives, you know, see how that goes. All right, this section here, we start off, and not this. Oh, too far. Right. We start off with energy, and for about the 800th time, okay, we start this chemistry discussion with energy, right? And we've defined energy, like I said, about 800 times. How do we define energy? The ability to
do damage.
Do damage, or the ability to move or change matter, right? The ability to make things different. Yes. Oh man, that was running from us. So, hold on. Does this Pat need it back? Or? It's not from us, Pat. It's actually from the office. Oh. Thank you. Yeah. I'll make sure that I clean it during 11th period. So when you come in, it's like the best. Nice. So, it's dry erase board cleaner, because we were commenting that I don't really have anything. I don't write on the board that often, but I never cleaned my board since it's been here, so it kind of looks dingy and dirty. So that's people helping you out right there. So. All right, the ability to move or change matter. And we've talked about kinetic energy, and we've talked about gravitational potential energy, and we've talked about chemical energy, and we've talked about activation energy, right? All of these things that keep showing up, right? Today, we're going to focus on thermal energy, the energy associated with the movement of microscopic particles that make up an object. The movement of microscopic particles that make up an object. The microscopic particles that we're talking about here could be one of two things. What are the two possibilities for the microscopic particles that we're talking about in this definition? Any good?
Atoms and molecules.
Atoms and molecules. Atoms if we're talking about what, Andy?
Elements.
An element. And molecules if we're talking about?
Compounds.
Compounds, right? Same ideas, right? Just are we talking about the same kind of element, or are we talking about our combination of elements? All right. Oh, one thing I forgot to highlight on the front page, right? Third period picked up on this, but down at the bottom here, right? Know your definitions in bold and underlined and with 4 exclamation points after it, right? A lot of the things that we're going to talk about today have very similar sounding definitions, but they are distinctly different from one another. And if you're not really careful with the definition, if something is asking you about the temperature, but you don't really understand what temperature means, it's going to be harder to answer that question. So make sure that you distinguish between these 3 things, because they sound very similar. So the first one we're going to talk about here is heat. Most of you probably know what heat is, right? I mean, it's the definition of a word you've used before, but in terms of its importance to matter and energy, heat is the transfer of thermal energy from one object to another because of a temperature difference. The transfer of thermal energy from one object to another because of a temperature difference. Transfer of thermal energy. Hopefully that definition sounds similar to another concept that we talked about earlier, the transfer of energy. We gave that a name way back when we first started talking about this concept. Anybody remember what we called the transfer of energy? It's work, right? So work is the transfer of energy. Heat is a type of work. It's just the transfer of thermal energy. So when we talk about a heat engine, it's transferring thermal energy, and in the process of doing that, right, It's doing work. It's energy flowing from one place to another. Now, specifically, how is this? It says transfer of thermal energy from one object to another because of a temperature difference. How is heat going to flow? If it flows because of a temperature difference, which way does it go?
Away from whatever has more thermal energy to whatever has less thermal energy.
So we would say because of a temperature difference, heat would flow from
High to low.
high to low, or if we're talking about a temperature difference, we would call it warm to cold, right? So heat flows spontaneously from objects with high temperatures to objects with low temperatures. Are we okay with the concept of spontaneous? What does it mean when we say that something is spontaneous?
Immediate and unexpected.
Immediate, unexpected. In this case, it also means that it happens on its own. We don't have to do anything in order to see that energy flow from hot to cold. Why? Well, a little bit later, or a little bit earlier in this unit, and in the next slide, we're going to talk about temperature. What did we say that temperature relates to as far as energy is concerned?
Movement of particles.
Movement of particles. So high temperature is going to relate to how much energy, Andy?
A lot.
A lot of energy. But we said that in nature, things flow towards low energy, right? So if energy flows from hot to cold, that's in line with our thinking along with this, right? If I have this tennis ball here, if I let it go, right, if I don't do anything to it, spontaneously, where is it going to head? Down. Why? Gravity, yeah, but if we talk about it from an energy standpoint, right?
There's less energy on the ground.
Specifically, what kind of energy, Jeremy? Potential, gravitational potential, right? High gravitational potential here. If I don't make it stay here, spontaneously, it will head there because that's low potential energy. Just like here, energy flows from high temperature to low temperature. Why? Because things flow from high energy state to low energy state. So it's real consistent with our thinking along, what we've talked about up until this point. All right, next, temperature. We've kind of talked about this already, right? Temperature equates to what when we're talking about the particles? Temperature measures for us what? The speed of the movement of particles. More specifically, temperature measures the kinetic energy of those particles, which is associated with their what? Kinetic energy relates to the what of the particles? Movement, okay? Which is the rest of that section there, right? The temperature measures the average kinetic energy of the particles, which is related to the movement of those particles, right? So on your outline, it says, you have this picture there, and right next to the picture it says, explain why the particles in the container on the left have shorter lines than the particles in the container on the right. The lines really didn't copy as well as I would have liked them to, but the same picture is showing up here on the board, right? So what do you see about the lines on the left versus the lines on the right? Which ones are longer? The right. Why? They're warmer. They have a higher temperature, and that means they moving faster. Good. All right. So put that into your own words. Colder temperatures, less kinetic energy, less movement. Warmer temperatures, more kinetic energy, more movement. Good there? So, we've used temperature in our definition of heat. Let's talk about why that happens. Why do things flow from high temperatures to low temperatures? Can be explained by using this picture of showing these two billiard balls, right? 9 balls, one with the white, one with the yellow stripe, and then 2 is the blue solid one. So 9 is coming in towards 2, right? 2 is at rest. 9 is moving, it runs into 2, and then 9 goes off this way, and 2 goes off this way. If we watch 9 before the collision and after the collision, what would we see about its speed, both before and after? What happens to 9 in the process of that collision? 9 slows down, right? But 2 started off at rest, and now it's moving. So what happens to 2's speed? It's sped up. In terms of temperature, right, what does that mean? What happened first? Is 9 representing a high temperature or a low temperature? High temperature, right? Because it's moving quickly. When high temperature things encounter low temperature things, what do? Yes, and that makes them colder. When cold things encounter hot things, what do? They gain energy, which means they become hotter, right? That will continue to happen until what?
They're equal.
Until they're equal. You know what you call that?
Low energy state.
It is a low energy state. Equilibrium. Specifically, this is called thermal equilibrium. All right? So, the little description there, right? It says, explain how the picture to the right explains the idea that heat flows from things that are hot to things that are cold. When hot things, like the fast-moving 9 ball, encounter cold things, like the stationary 2, what do? Hot things transfer some of that energy, and they cool down, right? But cold things gain some of that energy, and they speed up. So put that into your own words. Write it in a way that makes sense to you. Like we said, so things that were going fast end up traveling slower, things that were traveling slower end up traveling faster, until ultimately we find that all of them basically end up moving the same. And we call that idea thermal equilibrium, where all the particles that are in that mixture end up moving the same speed, therefore they are all the same temperature. Good there? All right, next, thermal energy. We explained it a little bit before, but same idea, just worded a little differently, right? The total amount of motion of all the particles that make up an object. Or we can think of it as the total damage that can be done, right? So, if we want to take into account the total amount of motion of the particles, what are we going to have to know? What factors are going to determine the thermal energy, or the total amount of motion of the particles? What are some things we're going to have to consider? That hand you're stretching. Okay. Speed, which relates to what measures the speed of an object? The temperature. So we got to consider the temperature. What else do we have to consider if we want to talk about the total motion? The what? The heat is more of an energy that flows from one to another. So So that may be occurring within there, right? But we said, as hot things speed up or hot things cool down and cool things heat up. So really the total energy that's there isn't going to change a whole lot. Does that make sense? Why heat might not be the most appropriate thing for this discussion? So we have to encounter temperature because that tells us how fast the particles are moving. What other factor might we have to consider if we want to know the total motion? That gets better. How fast they transfer is not really important as far as the total motion because they're just trading amongst one another, right? But that gets into heat counter. You're closer.
Traction? No,
Volume is closer.
State of matter.
And that's closer. The mass. That's the thing we have to consider, right? Because that's going to tell us what, Nick? Temperature tells us how fast the particles are moving. What does mass tell us?
How much there is.
How many particles are actually there? That's really important when we want to know how much total damage we can do. So, mass, temperature, and then Mark's state of matter does play a role in that, although the temperature does kind of relate to that, you know what I'm saying? Although that we have to take into the attractions a little bit as well, okay? But the amount of thermal energy that an object has depends on its temperature, its mass, and its state of matter. Because all three of those are going to be important in determining the total amount of motion. Good there? All right, first, let's look at this 4th of July sparkler. Question on your sheet. It says, do the sparks have a high temperature or a low temperature? So what, do the sparks have a high temperature or a low temperature?
High temperature.
High temperature, right? What does that mean? If the sparks have a high, the sparks that come off that sparkler, if they have a high temperature, what does that mean? They're moving fast and they carry a lot of energy, right? So those sparks have a lot, or the particles that make up the spark, right? The little pieces that come off of that, right? They have a high energy, they have a high temperature. But the next question says, do those sparks have a lot of thermal energy? So do the sparks have a lot of thermal energy? Mark?
No.
Not really, right? Because why?
There's not very many of them.
There's not very many of them, right? They have a relatively small what?
Mass.
Mass, okay? Yes, it hurts when they hit your hand, but in the big picture, do those sparks do a whole lot of damage to your hand? Not really, right? So yes, they have a high temperature, but overall, they don't do a whole lot of damage. The next picture of the bucket and the cup, I'm going to ask you to make an assumption, even though it does not look like it from the picture. It says, assume that the bucket and the cup have the same temperature. It says that on your outline, right? It says the water in the bucket and the water in the cup have the same temperature. What does that mean? So if they have the same temperature, that means that their particles have equal energy, and that means that from a movement standpoint, they are moving
This fast.
just as fast as pretty much just as fast as the particles in the other container, right? The particles in the bucket move as fast as the cup. Particles in the cup move as fast as the bucket, if they are the same temperature. But just because they are the same temperature, does that mean they will do the same amount of damage? Which one has more thermal energy?
The bucket.
The bucket, right? Because it has more
Mass.
right? So, just because two things have the same temperature doesn't mean they have the same thermal energy, right? know your definitions, right? And just because something has a high temperature, like the spark, doesn't mean that it has a lot of thermal energy, right? Know your definitions. Those are two different concepts, temperature and thermal energy. Good there? All right. Let's call that a day. I don't think we'll get through the other stuff by the end of the period, so let's wrap it up from there. Hey, 2 reminders, right? 1, make sure you get your course selection sheet done, right? See me sometime, either before school, after school, on lunch, et cetera, et cetera, et cetera. Okay? 2, I'll change the calendar over the weekend, make sure it's updated and has the right homework and reading and all that stuff.